In this video, we will continue our investigation of systems thinking, and we're going to be looking today at the work of Ackoff. Now, Ackoff was working, I suppose you could say, in quite the early days of systems thinking, and when he started his working, there wasn't a codified system of concepts that were related to thinking about systems in general. The paper we're going to look at today is Ackoff's attempt to formalize some of these concepts, not to shut off innovation, but to just give people the tools to start thinking about systems in general. You can see that he was writing in 1971. Moving to the introduction, the concepts and terms commonly used to think about systems have not themselves been organized into a system. An attempt to do so is made here. System and the most important types of system are defined so that differences and similarities are made explicit. And then, because Ackoff is also coming from a background of organizations, he's going to formally define some of the concepts of a system as it relates to organizations. The relationship between a system and its parts is considered, and a proposition is put forward that all systems are either variety increasing or variety decreasing relative to the behavior of its parts. This means that a system must actually change the information that flows through it in order for it to be effective. So Ackoff goes about then trying to define some of the concepts that are related to the systems approach. His broad definition of a system is given. The system's approach to problems focuses on systems taken as a whole, not on their parts separately. Such an approach is concerned with total systems performance, even when a change in only one or a few of its parts is contemplated, because there are some properties of systems that can only be treated adequately from a holistic point of view. These properties derive from the relationships between parts of systems, how the parts interact and fit together. So here Ackoff is saying that in systems theory we need to look holistically at the system by viewing only parts of the system and trying to optimize those. We will not necessarily get a better output from the system, because the system's goal as a whole is related to the relationships between those parts. So, in an imperfectly organized system, even if every part performs as well as possible relative to its own objectives, the total system will not perform as well as possible relative to its objectives. One must remember that at the time that Ackoff was writing, these concepts had not been defined into an agreeable system that people could consult to understand whether or not they're talking about the same thing. So he notes this here: despite the importance of systems concepts and the attention they have received and are receiving, we do not yet have a unified or integrated set of such concepts. So Ackoff then goes on to justify the reason for defining these terms. What we are really interested in is, what is Ackoff's actual definition of the concepts related with systems? And this here in point 1 is where he gives his definition. A system is a set of interrelated elements. Thus, a system is an entity which is composed of at least two elements and a relation that holds between each of its elements and at least one other element in the set. Each of a system's elements is connected to every other element, directly or indirectly. Furthermore, no subset of elements is unrelated to any other. Now, this is a very important part of the definition of a system. If you have a system that only relates two elements and there's no interaction with other elements, then those elements may be considered more or less the same thing, and there's no guarantee that the system is actually going to be acting on that information in any meaningful way. Also, each element in the system you must be able to get from it to another and all the other elements in the system via defined pathways. Ackoff goes on to define the notion of an abstract system, and in an abstract system, all of the elements are concepts, and this you can see in languages, philosophic systems, and number systems. Numbers are concepts, but the symbols that represent them, numerals, are physical things. Numerals, however, are not the elements of a number system. The use of different numerals to represent the same number does not change the nature of the system. In an abstract system, the elements are created by defining, and the relationships between them are created by assumptions. Such systems, therefore, are the subject of study of the so-called formal sciences. We are more concerned with the notion of a concrete system, in other words, a system in which we can see something happening. And it is only with such systems where we are concerned. In concrete systems, establishment of the existent and properties of elements and the nature of the relationships between them requires research with an empirical component. Such systems, therefore, are the subject of the study of the so-called non-formal sciences. Thus, in essence, Ackoff is saying here that the systems that systems theory are concerned with must have some kind of measurable property. If you cannot measure the property, then you cannot determine whether or not the system is actually processing the information that you're feeding into it. Remember that systems require an input and an output. The state of a system at a moment of time is the set of relevant properties which the system has at that time. So any system has an unlimited number of properties, and only some of these will be relevant to your particular research. If you go back to the view that we established earlier in terms of this evolution of systems thinking, then you will see that systems thinking evolved to deal with extreme complexity and also with multiple perceptions of reality. In other words, different perceptions or different views of a particular system are possible depending on what the goal of the system is and who is actually trying to model the system. So systems, in systems theory, as we are using it in terms of organization, you must be able to have properties, you must be able to note elements that will be part of the relationship between objects. The state of a system at a moment of time is the set of relevant properties which that system has at that time. Any system with an unlimited number of properties, any system has an unlimited number of properties, but only some of those are going to be relevant to a particular research objective. Okay. The values of the relevant properties that constitute the state of the system, in some cases we may be interested in only two possible states, e.g. off and on or awake and asleep. In other cases, you may be interested in a large or an unlimited number of possible states, e.g. a system's velocity or weight. So the state of a system at any given moment of time, when recorded, allows us to see how the system changes over time. Now all systems, or at least open systems, have an environment. And the environment of a system is a set of elements and their relevant properties, which elements are not part of the system, but a change in any one of those produce a change in the state of a system. Thus a system's environment consists of all variables that can affect its state. What Ackoff is saying here is that a system needs to receive input from its environment. It acts on signals coming from the environment and then processes those. External elements which affect irrelevant properties of a system are not part of its environment. In other words, there is no point modeling something which we are not looking to measure. The state of a system's environment at a moment of time is the set of its relevant properties at that time. The state of an element or subset of elements of a system or its environment may be similarly defined. And here's the important part, going back to the complexity of modeling systems. Although concrete systems and the environment are objective things, they are also subjective insofar as the particular configuration of elements that form both is dictated by the interests of the researcher. So this is basically saying that different observers of the same phenomenon will conceptualize them differently. And this is very important to systems theory because it allows you to build many different views of a particular system, depending on what it is that you are trying to model or measure. Ackoff then goes on to define the notion of a closed and an open system. A closed system is one that has no environment, while an open system is one that does. And we can have a quick look here at that. If you can see, in general, when you're conceptualizing systems, a system which is considered open sits within an environment and has some kind of basic interaction with that environment that flows across the system boundary. Whereas a system that does not have an environment is considered closed because it's not interacting or taking input from any environment. So they are completely self-contained. Systems may or may not change over time. A system or environmental event is a change in one or more of the structural properties of the system or its environment over a period of time and specified duration. That is a change in the structural state of the system or its environment. For example, an event occurs to our house's lighting system when a fuse blows, and to its environment when night falls. So these are changes that the system could then respond to. A static system is one to which no events occur. And we are not really interested in static systems. We are interested in dynamic systems. A dynamic or a multi-state system, one that has more than one state, is one to which events occur, whose state changes over time. And he gives an example. An automobile can move forward or backward and at different speeds. Such systems can be conceptualized either as open or closed. They close if elements react or respond only to each other and have no interaction with the environment. A homeostatic system is a static system whose elements and environment are dynamic. So a homeostatic system is one that can adjust itself to changes in the environment by changing its internal state. And a basic example of this is, for example, an air conditioner. At this point, I'd like to switch briefly to look at some of these in a visual form, some of these concepts, because visually it's always easier to understand concepts. So we will be looking at a model that we will be building in one of the practicals as an example. And the important thing here to realize is that there are many different ways of conceptualizing systems. But when you do so, it's best to choose a notation that's consistent and define different types of symbols which can be used to communicate your concepts. So looking at the basic definitions that we've looked at, we can see here a system known as the Smart Shopper system, and the system's goal is to model points that people accrue during shopping and to manage those as well as user information. You can see that the system has a designated boundary. The boundary encloses the system and all of its elements. The system has an environment, and in that environment a number of different properties have been designated. These properties become inputs, and the inputs flow across the system boundary. Once inside the system boundary, they will enter a particular subsystem. Subsystems then are related to one another. If you remember, going back to the definition, that a system must consist of subsystems which interact with one another. And all of these subsystems must be indirectly or directly connected to one another. In our diagram, we have designated a database management system as a central entity which collates the information and provides a standard interface for the other subsystems in order to store the state of the system in the database. So remember, we need to record the events in the system because it is only through that we can see the change of state of the system over time. You can see also that systems are providing output, the subsystems are providing outputs, and these outputs will move back into the environment. For example, an update of customer points which are printed out. The system also has a control mechanism in that it uses a feedback mechanism to reset the sales system in case of a failure. So in this one basic diagram, you can see many of the different aspects of a system. The system has an environment, a boundary, it has inputs and outputs, and it has subsystems which interact in some way to process the data that is put into it and to produce an output. Once again, the diagramming technique that we have chosen here is our own, and it's quite easy to see. If you browse for systems, you can see that just putting in the word system will return many different conceptualizations of a system. There's Google, that's the keyword system, and just a brief look at that, you can see that there are systems theory is applied to many branches of science, in fact to almost all of them, as well as to social sciences. So if you have a look here just briefly at any of these pictures, you will see that people have different notations and different ways of designating systems, depending on their complexity, depending on the view that they require of the system, and what they're trying to communicate, what their goal is. Okay, that's the end of the first part of the overview of Ackoff's paper. It is well worth going through this and reading through it and attempting to understand the different concepts in it.